Hi everyone. This is the promised video of conducting mixed effects meta-analysis in R. In my previous blog post and video, I covered how to conduct fixed effects meta-analysis as well as a random effects meta-analysis, and mixed effects is kind of a hybrid approach. There are three types of meta-analysis: fixed effects, mixed effects, and random effects. And there are three types of variance components in meta-analysis. The first type of variance is sampling error. This is something you can't get away from in any study you do, and you'll have in any meta-analysis you conduct. Basically, because different studies sample different people, and because people vary, you're going to have different total effects for studies simply because of the differences in who's in the sample. Fixed effects analysis assumes that sampling error is the only source of variance in overall study effect sizes. A random effects model assumes two sources of variance: sampling error and the random effects component, which is variance that appears to be systematic but is at the moment unexplained. In a random effects model, there are multiple ways to compute tau squared, the random effects variance component. The two main ways covered in the previous video are the Dear-Simonian-Laird approach, which uses method of moments, and restricted maximum likelihood, an iterative approach using maximum likelihood estimation methods. A mixed effects model assumes a third source of variance, the characteristics of the individual studies that may explain why studies find different total effects. These are known as moderators, variables you can measure and include in your analysis. When I presented results of a mixed effects meta-analysis previously, I always get a question about the use of this term moderator, because it appears it's being used in a different context than people are used to. A moderator is a variable that changes the relationship between the independent and dependent variable. You're saying that the effect of X on Y depends on M, the moderator. The way we assess moderators statistically is usually with some kind of general linear model approach, maybe a factorial ANOVA, which allows for interactions between categorical variables, or a regression of some kind, which allows for interactions between categorical and/or continuous variables. In the regression I conducted for my mixed effects meta-analysis, I didn't have any interaction terms, so people asked, do these variables actually fit the definition of a moderator? In a meta-analysis, the effect size is a numerical representation of the outcome of the study, which has the independent and dependent variables built into it. If you're using log odds ratio, this metric compares the odds of an outcome in one group versus odds of that outcome in another group. For standardized mean difference, or COINS-D, this metric presents in standard deviation units the difference in outcomes between your two groups. In a mixed effects analysis, when you add in moderators, you're looking for variables that explain why total effect sizes differ, why the effect of X on Y may be larger or smaller for different studies. So this actually does fit the definition of a moderator. It's just at the study level rather than the individual level. As a side note, you can include moderators in a fixed effects analysis, but a random effects model tends to be more theoretically justified. And the random effects variance component allows you to see if there is additional systematic variance that you don't have moderators to explain. There may be additional variables that differ across studies but aren't reported in study results, so you don't have a way to measure them. But remember that the output for fixed and random effects include metrics to show whether you have more variance than can be accounted for by sampling error alone. You'll have that with your mixed effects analysis output as well, so you can see if that additional random effects variance term is necessary. What kind of moderators might we want to include in our meta-analysis? There are some basic methods variables you can include, things like assignment method, random, matched, and so on, or whether the sample was composed of students or community. But many of the moderators of interest will depend on the topic of your meta-analysis, so it's good to be knowledgeable about the research topic or to have someone on your study team who is very knowledgeable about the topic. If you're conducting a meta-analysis on a topic you don't know well, the best thing you can do is start reading studies, getting familiar with the different methods used, and make some notes that can help you build your study codebook. You'll probably code more moderators than you'll end up using in your meta-analysis, and you likely do want to do this. It's better to code something you don't end up using than to realize later you should have been coding something all along, because now you have to go back and reread all of the studies you've already coded to get that information. Your codebook will of course change as you code, and that's also fine. The codebook is kind of a living document in the early stages. You'll just need to go back and recode previous studies coded with the old codebook. It's also a great idea to write a coding manual, which describes how to use the different coding categories and variables and any coding decisions you've discussed with your partners. For example, I conducted my meta-analysis on pretrial publicity effects, which is any information in the media that may bias potential jurors, and I looked at the effect on guilt outcomes, which were operationalized in a couple of ways, as a continuous guilt rating or as a dichotomous guilty-not guilty verdict. Here's my data dictionary, which basically pulls in information from the study codebook. The codebook itself was a form that we used as we read through the study so we could check off categories and fill in details. So to briefly go through the different moderators, at the top here is really just identifying information for the study. A report identification number, the study number within the report, the names of authors, year of publication, and whether information on that study came from a journal article, a dissertation, and/or some other source, such as a conference presentation and book chapter. Some studies came from multiple sources because people might do their dissertation on a topic and then later publish a journal article based on that dissertation. Underneath that are the moderators that I used. First of all, we coded source of the sample, and I can zoom out so you can get a better look at what the different code categories are. So many studies used students, but some used a community sample. Some used potential jurors, which means that before people could qualify for the study, they were asked if they were registered to vote and therefore were eligible for jury duty in that jurisdiction, as well as studies that used real trials, which we coded as actual jurors. We coded on group assignment, whether it was a correlational study, as was the case in studies using real trials, or whether they used random assignment to decide what pretrial publicity people should be exposed to. We coded the instructions the control group received, whether that was general crime news, neutral news about the crime of interest, what kind of case it was, a civil case, homicide, a sexual assault case, a small number that used another violent crime besides homicide or sexual assault, a nonviolent crime such as burglary or breaking and entering, or an unknown crime or combination of crimes. We coded whether people were asked to provide a verdict or a guilt rating before reading the trial or hearing the trial, and whether they provided that same verdict or guilt rating after the trial information. We coded on the trial presentation that people received. So for studies that only looked at the biasing effect of pretrial publicity without hearing any trial information, it was coded as 0, no trial. Some received a summary of the arguments of the trial. Some received an actual transcript of the trial. A small number used an audio recording or a video recording of a mock trial. 5, what we called mock, was when the trial was actually acted out in front of participants, which very few studies did. And then lastly, whether the study used an actual trial. One of the major moderators we were interested in was strength of the evidence, whether that was weak, moderate, or strong. In Calvin and Zeisel's The American Jury, they talked about the liberation hypothesis, which means that when the strength of the evidence is weak or strong, people will use the information from the evidence to determine guilt. But when it's moderate, when the evidence is ambiguous, that's when people use outside information, things like the attractiveness of the defendant or pretrial publicity. We also studied a group of variables that are meant to ameliorate the effects of pretrial publicity, so a delay between hearing the biasing information and actually receiving the trial. Whether the study used voir dire, which is the questioning of potential jurors to determine if there are any sources of bias that might preclude them from being involved in the jury. Whether they received a judicial admonition that told them specifically to ignore any outside information besides the evidence, including pretrial publicity, or whether they just received the standard jury instructions. And then finally, we coded whether participants were allowed to deliberate before providing a verdict. Remember that statistics is all about explaining variance, and so we're using moderators to try to explain some of that variance. When you learned regression in your statistics class, you probably learned what's called ordinary least squares regression. Least squares means the regression equation is trying to minimize the squared deviations between the predicted outcome and the observed outcome. So you want your coefficients in your regression equation to generate a predicted value as close as possible to the observed value. This is an unweighted analysis, so every case included in the model is weighted equally. Meta-analysis uses weights, so studies with smaller variance, more precision, get more weight than studies with larger variance or less precision. Meta-analysis regression or meta-regression uses weighted least squares. Just like other regression models, you want to be careful about how many predictor variables you include, and you want to make sure that your predictor variables aren't too highly correlated with each other. We refer to this statistically as multi-collinearity, and it means that you have multiple variables trying to explain the exact same proportion of variance. After you finish coding the study, you may find that some of your coded variables always hang together. For example, method of group assignment was highly correlated with, for example, trial presentation method. Control group instructions was also highly correlated with some of those variables. You wouldn't want to include all of those variables in the same analysis because they assess the same thing and they could be considered proxies for each other. The best way to examine this is to look at frequencies and correlations between your moderators. Today, I'm going to demonstrate mixed effects analysis using the log odds ratio results and a handful of moderators. All of the studies I'm including in this demo obtained verdicts after presenting trial evidence in some format, though some also measured verdict or guilt pretrial as a way to assess whether the pretrial publicity is actually biasing people. As with the previous meta-analysis posts, I'll be using the metafor package today, but I'll also be using the ESC or effect size computation package for a few things. Big thank you to Deeply Trivial reader Fred Oswald for sharing information on that package. So this first file that I'm loading is the study information. That's the coded information about those studies, which includes those moderators. The second file are the actual dichotomous outcomes, which we'll use to compute our odds ratios. You'll notice that my study info data file includes 100 observations, so that's how many studies were included in the full meta-analysis. Only 53 of those included outcomes that could be used with an odds ratio, and all of these were post-trial. I pulled in the tidyverse package so that I can quickly merge those two data sets together, matching on study ID, and I now have those additional 32 study info variables included. So just doing the same process as before, we'll load the metafor package, and we'll compute our log odds ratios for those data. Now, if I view my OR moderators dataset, which is the full dataset with the odds ratios as well as our moderators, there were two studies that didn't include information to calculate odds ratio in the same way as the rest of the studies. You'll see we have an NA here and also here. So if we scroll over, this one, the only information they gave was that the chi-square was not significant. The other study gave a chi-square which was significant, as well as Kramer's V, the effect size for chi-square, but it didn't give me the number of guilty outcomes for the treatment group or the control group. But I can use these chi-square values for these two studies to fill in that missing information. And that's where I'll use the ESC package. So for the ESC package, I'll be using the ESC chi-square function, which allows you to compute, in this case, a logit or a log odds ratio using a chi-square value and the total N of the study. And that gives me a list, which I can view. And I have my effect size, which is a log odds ratio of 3.31, and my variance, which is 0.574. So I can fill those in to those NA spots in this way. This is the nice thing about having a named list, is that you can still access them with the name of the list, the $ operator, and then the name of the list item that you want to include. So I'll do the same thing here for this study that found a non-significant effect. When a chi-square is non-significant, the expected value is equal to the degrees of freedom. Expected chi-square is 1. And the total sample size for that study was 849. So I'll just do the same process here, compute that, and fill in those values. So now I have a complete data set. And you'll notice when I scroll through, I no longer have any missing values in my yi and vi variables. So the very first one I'll compute here is just a random effects model. And I can take a look at the summary of that output. So just looking at this once again, I have my tau squared estimate, my random effects variance component. I have an I squared, which tells the proportion of variance that is not accountable by sampling error, which is about 73.5%. So a random effects model is definitely justified in this case. And my Q statistic, my test for heterogeneity, also confirms this result. So this gives me an overall estimated log odds ratio of 0.7102. But this doesn't tell me whether my moderators explain why studies might find bigger or smaller effects than this overall estimate. So this next analysis I'm going to run includes this extra mods argument, which are my moderators. So first of all, whether people were asked to render a verdict pre-trial, whether it was a homicide case or some other kind of case. 2 dummy variables for strength of evidence, one comparing moderate to weak and strong, and the other comparing strong to weak and moderate. And finally, whether people were asked to deliberate, because the argument that the courts make is, yes, pretrial publicity might be biasing, but because people are allowed to deliberate, that should ameliorate those effects naturally. So once again, let's look at the summary. And you'll see now, in addition to having the same things I had before, my tau squared, my I squared, my Q statistic, I also have information on the moderators. First of all, you'll see that my I squared is smaller than it was before. This is corrected now for the variance that's being accounted for by the moderators. So a random effects model is still justified here, but the moderators are explaining a proportion of that variance. And we'll see here we have this R squared, which is the amount of heterogeneity accounted for. Our Q statistic is corrected now, taking out the variance that's been accounted for by the moderators, but it is still significant. So once again, a random effects model is still justified in this particular case. But my Q statistic testing my moderators is also significant. So this is telling me that I have significant moderators that are explaining why study effect sizes might be larger or smaller. If we scroll down here, we have model results. These are just regression coefficients. So first of all, you'll see that pretrial is significant and it's a negative coefficient. What this means is that studies that ask people pretrial what their verdict would be actually find smaller post-trial effects. Second, homicide is significant. Homicide cases tend to find larger pretrial publicity effects. And then finally, strength of the evidence moderate is significant. Once again, studies that use a case with moderate evidence or ambiguous evidence tend to find stronger pretrial publicity effects, which confirms the liberation hypothesis from Calvin and Zeisel. Deliberation actually doesn't have a significant effect. And as we would expected, the dummy variable for strength of the evidence strong doesn't find a significant effect. So there we have it, conducting a mixed effects meta-analysis. I'll be sure to include all of my code as well as the sample data set that you can play with to practice doing this on your own. And in a future post, I hope to talk about some different ways of presenting meta-analysis results, writing them up, as well as how you might present the results of a mixed effects meta-analysis visually. I hope to make some more videos soon, so stay tuned. Thank you so much for watching.